At the beginning of the 20th century, scientists were at odds over the nature of light. Thomas Young's double-slit experiments in 1802 and James Clerk Maxwell's famous equations provided strong evidence that light behaved as a wave. However, Albert Einstein's theory of photoelectric effect supported the idea that light behaved as a particle. So which approach is correct? Is light a wave or a particle? The answer is both.
Wait a minute. That doesn't make any sense. How can something be two completely different things at the same time?
To understand this wave-particle duality of light, let's take a look at Schrödinger's cat. Schrödinger's cat isn't actually a real cat. It's a thought experiment proposed by scientist Erwin Schrödinger. In this made-up scenario, a cat is sealed inside a box. Inside the box is a radioactive substance and a setup that will kill the cat if the substance decays. We as observers can't see the cat and don't know if it's alive or dead when it's inside the box. The idea is that inside the box, both possibilities are true. The cat is both alive and dead at the same time. However, once we open the box, the cat is forced into one of the possibilities and will appear either alive or dead in the moment that we view it. The same principle is at play in wave-particle duality. The wave isn't actually a tangible object. It's an area that represents all of the possible positions of the light particle, also called a photon. When it's observed, light is forced to choose one position as a photon at any point along the path of the wave. However, when it's not being observed, light can be both a wave and a photon. This way of thinking about wave-particle duality is known as the Copenhagen interpretation. Although it's one of many interpretations, it's one of the most popular ones from the last few decades. But wave-particle duality isn't just a property that applies to light. It's a property of all matter.
Wait, that's impossible. Wouldn't that mean there would be a wavy?
Yes, it does mean that. However, thanks to de Broglie's law, we know that the larger an object is, the smaller the wavelength of its atoms. This means that for an object the size of a human, or even something much smaller, such as a grape, the wavelengths of its atoms are way too small for us to see, meaning that we can't really observe its wave nature. At first glance, this might seem like a concept that is completely unrelated to our daily lives. However, wave-particle duality is a cornerstone of quantum physics, which is directly responsible for the way that we live our lives today. The sensors, computers, and other technologies that are so important to us couldn't have been created without the principles of quantum physics. But quantum physics is also important to our future. In fact, the very idea behind wave-particle duality is one that we can take with us moving forward. The idea that there are an endless number of possibilities out there, and we can find them if we just keep looking. Thanks for watching.